Welcome to another seminar belonging to the IRENA online conference series. This time the presentation is entitled Indirect and Direct Measurements for the S process, presented by Dr. Philip Adsley. Phil is an assistant professor at Texas A&M University in the Department of Physics and Astronomy at the Cyclotron Institute. He studied natural science at Cambridge before earning a PhD at the University of York. He then spent 2 years as a postdoctoral researcher at the Itemba Labs in Cape Town, followed by another 2 years in IPN Orsay in Paris. Subsequently, he became a Claude Lyon Fellow once again at Itemba Labs, affiliated with the University of Witwatersrand before accepting his current position in Texas. This move came with an upgrade in salary, but a notable decline in the quality of the local wine. That's Phil's words. His research interests include understanding neutron stars through studies of Taiwan X-ray bursts and photoabsorption reaction, S-process nucleosynthesis, and pollution in globular clusters. So now, without further ado, let me hand it over to Phil to begin the section. So Phil, the floor is yours.
Thank you very much. So it's a pleasure to have been asked to give this talk today. Those astute among you may notice that there is a Canadian flag behind me. I'm currently at Triumph in the cafeteria, so hopefully there's not too much chaos goes on in the background. We're here running an experiment, which I will briefly discuss as part of the talk. So the things to cover today, what is the S process and what the S process is, because there's really more than one. What are they? Why do they matter? I know that this is a mixed audience. There's people here who are not nuclear physicists, and so I want to talk a bit about how the nuclear data that we get from experiments go into astrophysical models.
I think the connection was lost.
Am I back?
Okay.
Okay, sorry, I don't know where I cut off, so I'll start again with this slide. Thanks, Hesh. Okay, so the S process is one of the sources of the elements in the universe. So we have this periodic table, which shows...
Sorry, Phil, you can share your screen, please?
Okay, I'll try again. It apparently bumped me from the network. I'll try again. Okay.
Yeah. Good.
Okay. We'll try that again. So we're trying to explain the origin of the elements. We have this nice periodic table from Chiaki, which shows the different sources of the elements from different processes, including, for example, the main S process in AGB stars. So the S process, what's happening is we capture a neutron, and the timescale for neutron capture is much slower than the beta decay. And so we capture a neutron, we beta decay back to stability, and then we capture another neutron. And we go through that process many times, and we can make many of the elements heavier than iron, up to you can see lead and bismuth at the end of the main S process. So there's two main sources of neutrons, alpha capture on carbon-13 and alpha capture on neon-22. And both of these produce neutrons. If we have more neutrons, and that might be because we have more carbon-13, we have more neon-22, it might be that the reaction rate for these neutron-producing reactions is higher, we can make more heavier elements. But it's not just the number of neutrons that we make that tell us how many heavier elements we have. It's also the number of neutrons that we lose to other processes. So they can be absorbed on other stuff. Magnesium-25, for example, is a neutron poison. And that prevents us from making some of the heavier elements. Now, notably, you can see in these plots that for the green, the kind of lime green, there's a bit of a delay before we start to make some of the elements in the main S process, because AGB stars live for a bit longer and they take a while to start enriching the galaxy and the S process elements that they've made. There is another S process known as the weak S process, which takes place in massive stars, which burns up to about the mass 90 peak. So this is zirconium, strontium isotopes, something like that. But in recent years, and I noticed that Raphael is here and he has been one of the people leading this, there's been this discussion of an enhanced S process, where a rotational mixing in stars can mix the products of the helium burning core and the hydrogen burning shell together. And this can increase the efficacy of the S process because it allows more of these S process sources like neon-22 to be made. And this can, in theory, then produce some heavier elements at masses above the weak S process peak fairly early on. Now, there is some observational evidence for this, and I think if you look in, I think it's Arthur's paper that's listed on this slide, you can find more of the references for this observational evidence. But there are, for example, some S process enriched stars where the abundances are consistent with some of these rotating models. Some metal poor stars, which means old stars, with some of these S elements that are found in the halo of the Milky Way, and stars for which AGB stars could not have contributed the S elements because they're too old. The AGB stars haven't been able to contribute this yet. Also, some carbon-enhanced metal poor stars, which also show S elements in their atmospheres, which are not in binary systems. In binary systems, there's a different process that can cause this, but for solitary stars, that's not really the case. So we have these S processes going on and they're making stuff. So what information do we need to know? Well, we know that the source of the neutrons in this case is mostly neon-22 alpha N. And we know not only that we care about how many neutrons we make by the neon-22 alpha N reaction, but also how many neutrons we lose to other processes. And one of the important processes that removes these neutrons is capturing a neutron on oxygen-16 to make oxygen-17. So we now have oxygen-17 and a load of alpha particles. And if we have the oxygen-17 alpha N reaction take place, this means that the oxygen-17 liberates a neutron again. We get the neutron back and we can do nuclear synthesis with it. However, if the oxygen-17 and the alpha particle fuse and emit a gamma ray and make neon-21, then we've lost that neutron. And so if we know the relative strength of the oxygen-17 alpha N and oxygen-17 alpha gamma reactions, we can get some constraint on how many neutrons are recycled, and more neutrons recycled means more S process. And so there's an example from Matt Taggart's PhD work showing. Yeah.
Sorry to interrupt a little bit. There seems to be a lot of noise in the background, and so it's a bit hard to hear you. If you could speak up a little bit.
I'll try to speak louder. Yeah. Okay.
Yeah.
So yeah, it's unfortunate that I just had to find somewhere to try to do this. So so what happens is then if the oxygen-17 alpha gamma rate is weaker, then more of the neutrons are recycled, and because of that, we have a more efficient S process. And you can see here, the black line is with a rather high oxygen-17 alpha gamma rate, and then by reducing that alpha gamma rate, it can cause more significant nuclear synthesis to higher masses. And so you can see that it's now extending beyond the strontium zirconium region up into the higher mass region. Now that's the astrophysical background, but what we also care about is the how do we get these nuclear reaction rates that are used as inputs for the reactions. And so we want a nuclear reaction rate, which is effectively how fast do these reactions happen in stars? Are they happening very quickly, very slowly? So we know a stellar plasma, the distribution of relative energies of the particles follows the Maxwell-Boltzmann distribution. That part's easy. And then at each energy, we know there's a probability that a reaction takes place, and we call this the cross-section. And this depends very strongly on the penetration of the particles through the Coulomb and angular momentum barrier. And then what we do is we take our probability of interaction at each energy, and the probability of two particles having that relative energy, and we add up all of those probabilities, and that gives us the total reaction rate. Now, there's, you have to eventually do this numerically. There's a load of kind of difficulty in how to do this, but fundamentally the nuclear physics input here is the cross section. That's what we need to calculate, and that's what will allow us to get the reaction rate. Now, for these reaction rates, there's two main ways that they happen. There's direct capture, which is into some bound state directly through a single step. Those are typically not so strong, and so for most of the reactions that we care about, we need to know about the resonance reactions that are taking place. And these go through some excited nearly bound state in the compound nucleus, which then decays into the reaction products. These resonances are characterized by certain parameters, things like the energy of the state, the spin and the parity, and the partial widths, decay rates into different channels. And so if we know what these parameters are, we can calculate what the cross section should be, and then we can calculate what the reaction rate should be. Okay, I just want to briefly mention partial widths because they're important for the discussion of some of how we use some of the reactions that we use to determine the reaction rates. So these partial widths, we can kind of split them into two parts. There's one part which is the nuclear structure part, and it tells us how much like that channel some compound nuclear state looks. And on the other side, there's a penetrability. This is the probability of having some fusion take place through a barrier. Remember that stars are quite cold compared to the Coulomb barrier, and so you have to kind of make your fusion reaction is all stuff that's taking place below the Coulomb barrier energy. And we can put these things together, and as a really important point, the angular momentum barrier it has a big effect on the penetration factor. And so nuclear astrophysics, we really care about low spin states. If we know that a state has a high angular momentum barrier, it's not going to be important for nuclear astrophysics. And so we can use information about, say, spins and parities of states to limit which states we care about for our nuclear astrophysics. And just to demonstrate this, I have a plot showing from different angular momenta, orbital angular momenta, the penetration factor. And you can see that it drops by many orders of magnitude when you go from no angular momentum to a high angular momentum for the system. So that's a little bit of just nuclear physics background. But what we care about, what do we need to find out? What do we need to know? So ultimately, what we would really like to have are direct measurements of cross sections at every energy, which can be converted into reaction rates. However, if we don't know or we can't measure those cross sections, and I'll come back to that, we can instead calculate the rate if we know these properties of the resonances: energy, spins, parities, partial widths, for all of the relevant channels that we care about. And all of those properties we can determine through indirect methods. So some of you will have seen this, my favorite slide before, because I think that it's useful to kind of talk about the hierarchy of needs for nuclear astrophysics. So often in nuclear astro, we have to answer questions about how many states there are and what energies those states are at and what spins and parities they have, because those are basic questions which allow us to say, do we care about this state? Is it important for nuclear astrophysics? And then for some spectroscopic information, which is giving us actual cross sections, actual kind of real contributions to the rate, those are kind of higher order questions. Once we know a resonance is important, we can try and measure some of these more difficult factors to determine. But if we can rule it out as unimportant or know that there's no state exists which needs to be measured, we can limit the amount of work that we have to do in our calculation, in our experimental work quite significantly. For direct measurements, these are in theory relatively easy. They are in practice extremely difficult. So what we want is the cross-section of a function of energy. So we fire the beam at the target at a particular energy and we measure how many reactions take place. If we know the number of beam particles, we know the number of target particles, we know our efficiency, we know our cross-section. However, these measurements are extremely challenging because the cross sections are extremely low, because the energies are very small relative to the Coulomb barrier. And just as a nomenclature thing, we sometimes talk about, for narrow resonances, the integrated cross section, which we call the resonance strength, and I'll talk about those a bit later on, just so that you. But I just wanted to mention it so that you knew what I meant. Some of the indirect tools we have for these reactions can include things like inelastic scattering. These mean that we can find out things like energies and spins and parities of states. Gamma ray spectroscopy, which allow us to get energies, branching ratios, spins and parities. And also, for example, this experiment that was done at TAMU a few years ago, transfer reactions, which can also give us things like energy, but can also allow us to access pieces of information like partial widths and spins and parities as well. So that is some of the nuclear physics background. Now I'm going to talk about two transfer reactions in this talk, and so I want to try to explain what these reactions are, so that you're familiar and you understand how we can use these transfer reactions to get some of this nuclear physics information. So they're reactions in which something is transferred. I think that should be obvious from the name, but I wanted to say it. Now we do these reactions so that they're peripheral. They're reactions which are happening at the nuclear surface. They're kind of glancing blows, and they should happen quickly. So when something is transferred and the thing that it was transferred from should leave the reaction before it can undergo other reactions. So we want our transfer reactions to be dominated by a single step mechanism. We don't want it to be something confusing where there's lots of stuff going on. We want it to be a simple single step mechanism at the nuclear surface. And there's two really useful bits of information we can get here. One of them is that the shape of the differential cross-section, how likely the reaction is to take place at different angles, tells us about the transferred angular momentum from the system. And the amplitude of the differential cross-section tells us something about the structure of the excited state populated in the transfer reaction. So it looks like some core plus the transferred thing with some probability. So someone's ringing a phone, which is unfortunate. But, so for these spectroscopic factors, which I will talk about just as a brief thing to mention, these are effectively a normalization factor. We do some single particle calculation. We assume that the transfer reaction is with a single particle structure, and then we normalize our data to the experimental data to the single particle calculation with this spectroscopic factor. Now, the spectroscopic factor isn't real. It's a kind of convenience in the models, but it allows us to it allows us to see how much like the single particle structure, that excited state in the nucleus, looks like. But they have another use, which is that they allow us to calculate what the width is. Now, there's some maths on here which I don't need to obsess about, but what the spectroscopic factor is telling us is how likely it is that the decay we're interested in appears at the nuclear surface. Remember that the transfer reactions are peripheral, so the probability of the transfer reaction taking place is proportional to how likely the transferred particle is to appear at the nuclear surface. And that same factor, how likely that particle is to appear at the nuclear surface, is also comes into the partial width. So how likely that state is to decay by that particle emission it's the same factor that's coming in there. And so by measuring the transfer reaction and getting the amplitude of it, we can tell how likely we are to have that particle at the surface. We know how we can calculate how likely it is to get through the barrier, and so we can calculate that decay rate. And this is the piece of information that we need for our calculations of the reaction. So by combining, by taking this transfer reaction, we can then determine what the width is, and it's effectively just what is the scaling at the surface of the nucleus. So very briefly, neon 22 alpha N is a very important reaction. It tells us how many neutrons are made for the S process. These reactions are very well studied, but there are some important uncertainties in these reactions. So this is from the evaluation that we did a few years ago, showing the differences between different recommended rates based on different nuclear data sets. And you can see there's this significant reduction in the alpha N rate based on the updated measurements from Texas A&M a few years ago, and also some discrepancies in the alpha gamma reaction based on some different observations. So there are a number of efforts underway to measure the properties of some resonances relevant to these reactions, including some measurements at LUNA. The measurement that we're currently doing at TRIUMPH is also trying to constrain this neon 22 alpha gamma reaction better. And also there's this absolutely critical resonance for the alpha N and alpha gamma relative strengths at 832 keV, 706 keV, where the relative branching into the gamma particle neutron emission is critical, and there's a number of experiments focused on this at the moment. I think there's one currently finishing at LUNA. We have some planned measurements at A&M as well. So I did say I was briefly going to cover the status of this reaction, and that is how briefly I'm going to cover it, because the main focus of what I want to talk about is on these experimental studies of oxygen-17 plus alpha reactions. So I'm going to tell you what my conclusion is now, which is that we should do more experiments where we combine different indirect techniques, because it's really useful. We can use the different selectivities of the different reactions to constrain our cross-sections much better. And so using lots of different tools to approach the problem from different directions is much more powerful than just one experiment. So the experiments that I'm going to discuss are an experiment with the neon 20 DP reaction that was done with the split pole spectrometer at Tunnel, a direct measurement that was done with Dragon here at TRIUMPH a few years ago, and also a transfer reaction that we did with the Munich Q3D that was recently published, and I will actually mention some upcoming measurements at the end as well. Now, Cameron kindly sent me some slides, and I stole this one because I thought it was a really nice summary of of the problem, and also he stole it from Allison in the first place, so I feel it's justified that I can take it from him. So there's these 5 different experiments mentioned here. I'm not going to discuss the Helios one, but you can see that they have different aims. They're aiming at different pieces of nuclear data. And so what we can use is effectively different experiments are sensitive to different parts of the nuclear data. And by combining them, we can get all of the parameters that we need. But you can notice, for example, that the Q3D measurement is sensitive to the J-pi and the alpha particle partial width, but not really sensitive to the other properties. So this measurement by itself can't do everything that's required. It has to be combined with the Dragon measurements and the tunnel measurements and the EMMA measurements and Helios measurements. They all have to be combined to give a complete picture. So the first experiment was performed at the Triangle University's Nuclear Lab Tunnel in North Carolina. This used a deuterium beam, so a proton and a neutron, on a neon-20 implanted carbon target. And we get the DP reaction taking place. So this is transferring a neutron from the beam onto the target. And the protons that come out from the reaction go into the spectrometer, and they are bent according to their energy. And so if they're lower energy, that corresponds to a higher excitation energy. They hit the focal plane over on this side because they're bent more easily by the field. If they are higher energy, they go off to the other side. And so position on the focal plane is excitation energy. And the results look something like this. So you can see this is taken from the PhD work of Joseph Frost-Schenk. And you can see that there's a number of states populated. You'll also notice that there's a significant continuum, and there's also some other states kind of lumps on the focal plane that are from background, from contaminants, from different things on the target. And so what one can do is you can see these states, you can extract yields at different angles, and for example, these are just curves plotted to show to guide the eye. You can see that the shapes of the differential cross sections are very different based on different angular momentum transfers, and so one can use these differential cross sections extracted from these data to constrain the spin and the parity of the state in neon 21 populated in this reaction. I mentioned previously also that by extracting the spectroscopic factor, we can extract the partial width. So in this case, we can extract both the spin and parity of the state and the neutron width for the excited states in neon 21. And this allows us to work out, are they more likely to decay by neutron emission or by gamma ray emission? And thus, what is their contribution to the alpha gamma or alpha N reactions likely? As a general rule, this is very hand wavy, but this is a general rule. If we see a state in a DP reaction and it's got a low spin, then the neutron width is going to be higher, and so the alpha N reaction for that resonance will dominate over the alpha gamma reaction. We did calculate neutron widths from this comparison with the DWBA. Take the differential cross section, you can go and calculate what the DWBA comparison is. And if the neutron width is much larger than the gamma ray width, then we know that for that resonance, we will recycle the neutron, we will get it back, and the S process will be more efficient. And at the end of this experiment, and with all of the calculations and everything done, we had these ratios between the reaction rates over here. So this is the alpha N over the alpha gamma. And you can see that the line is just to show you where 90% of the neutrons are recycled. The black line is the 50% coverage, and the 1 sigma lines are the red dotted lines. And you can see that we favor, especially at higher temperatures, quite a strong neutron recycling. But the problem is that in the region that we're interested in, for the S process, which is the kind of 0.2 to 0.3 gigakelvin region, we have this extremely high uncertainty, where we're not really sure how many neutrons are being recycled. And the problem here is that while we know how each individual resonance is likely to decay, is it more likely to decay by gamma ray emission or by neutron emission? We can't actually, we don't actually know how likely each resonance is to be populated, because we need the alpha particle partial widths to do that. So there's a large uncertainty here. We need the alpha particle partial widths, or some related information for the alpha particle partial widths. So the next two measurements I want to discuss are approaching those problems. So one of them is the Dragon measurement that was done here, and the second one is the transfer reaction with the Munich Q3D. For those of you who are not familiar with Dragon, the beam comes in, and there is an array of BGO detectors around the target position. There's a windowless gas target, and the gamma rays produced in the reaction hit these detectors around the target. And the particles, the heavy particles which are made, in this case, the neon 21 recoils, travel through the spectrometer, and they're separated by a set of magnetic electric dipoles. They're transported through, and they hit a focal plane detector over here, which consists of an MCP and a DSSD. And so you can see, for example, this nice cluster of particles here, which corresponds to neon 21 recoils, and also a plot here showing how long it takes the particles to travel through the spectrometer. So this is the separator time of flight. It's the time between something hitting the BGO array and something hitting the focal plane. And so you can see for different resonances, some really nice clean peaks with very little background. And then for one of the resonances, there's no counts at all in the region of, well, there's 2 counts in the region of interest. So this is not really a signal. It allows an upper limit to be put on the resonance strength for this case. So this is all the work of Matt Williams, who's now at the University of Surrey, but was at Triumph at the time. And you can see, compared to the previous evaluation of this rate, which was done by Andreas, there's a significant reduction in the strength of the oxygen 17 alpha gamma reaction. And the reason why there's a strong reduction in that strength is because there's now limits or measurements of some of these resonance strengths. And so we know that they're smaller than they were guessed to be. There was no experimental data. And so with new experimental data, it's able to show that there's this reduction in the rate. But you can still see here that in the 0.2 to 0.3 gigakelvin region that we really care about, there is still a significant uncertainty in the in this reaction rate caused by unknown nuclear data. And so we still need to get alpha particle widths, and you can already see that at the lowest energy with Dragon there was nothing seen, and so we have to go back to indirect techniques. We can't use these direct measurements at these very low energies. There's just no cross section. There's no observable signal. And so we did this using the Munich Q3D. This is another magnetic spectrometer of blessed memory. Unfortunately, it's no longer, the lab at Munich has closed. And in this case, we were using tungsten oxide targets enriched in oxygen 17. So we used a lithium-7 beam, which is, you can think of lithium-7 as being made from an alpha particle plus a triton. And what happens is you transfer the alpha particle onto the oxygen 17 as a proxy for the oxygen 17 capturing onto the alpha particle. You get a triton come out and you detect that triton. And again, focal plane position corresponds to excitation energy. Now there's a kind of a trick here, which is because we used tungsten oxide and we used relatively low energy lithium-7, the Coulomb barrier for the tungsten, reactions for the lithium-7 and the tungsten is quite high, and the beam energy is below that. And what it means is you don't really get reactions on the tungsten in the target. You just get reactions on the oxygen, which is enriched in oxygen 17, but there is oxygen 16. There's also water on the targets. There's carbon backing. So there is contamination in the targets, but we can avoid some of those reactions taking place on the tungsten. It's much cleaner. The problem that comes about from it is that the tungsten causes a degradation in the energy resolution, and so the energy resolution isn't nearly as good as it would be without the tungsten in the target. Again, we can do the same process that we did with the DP, but we can do this with the differential cross-section, and so we can take the differential cross-section, we can do a DWBA analysis, we can extract the alpha particle partial widths. There's some limitations with oxygens, with lithium-7T reactions. They tend to give, as you can see here, reaction distributions which are kind of more featureless. They've not really got strong structures. They drop off, but it's not really got kind of characteristic shapes so much. And also because oxygen-17 has spin, there's different angular momentum contributions that can take place for the different that can couple to the different final states. And so the analysis is harder than if it's for an even nucleus where there's no spin. This is a slightly more complicated example. Nevertheless, the alpha particle partial widths can be extracted, and all of these things can be put together. So the results from the Munich Q3D, from Dragon, from the experiment with the tunnel split hole, as well as any literature data, can be put together to evaluate what the reaction rate should be. And this plot shows those results. And so this is from the recent paper by Ferouz Hamash and me and Livio and a lot of other people. And you can see that there is now, the top two plots are important, but I want you to focus on the bottom one. So you can see the previous measurement from the tunnel measurement, that's in the green, where there's this significant uncertainty in the region of interest between 0.2 and 0.3 gigakelvin in the ratio of the reaction rates and how many neutrons were likely to be recycling. And with the new alpha particle widths, we end up with the black curve, and you can see that now the uncertainty is much smaller, but also that the reaction rate ratio really strongly favors a really strong neutron recycling. So we're getting most of the neutrons back, and we can see what impact that has on the S process. So these calculations were done by Arthur, I think, and Chopin, and these are using a post-processing model. So they have taken a model, a kind of a simple 1D model, which they've calibrated against 3D models, so that they can use this to quickly calculate the effect of the S process without the computational expense of putting it into a model with full rotation. You know how the rotation should take place, and you can stir up your system to mimic that rotationally induced mixing, and also by injecting carbon-13 and nitrogen-14 in as the forces for carbon-13 and neon-22 for the S process. And so the figure here shows if you took the previous rates, which didn't have such a lot of information on the low energy resonances, what the production of the S process is above strontium. You can see that it's relatively small, but with the new rates on oxygen-17 alpha N and alpha gamma, this boosts the production in this region above strontium quite significantly. There is still some uncertainty because there are still some uncertainties in the reaction rates, but certainly with these new data, we favor much stronger neutron recycling and a much more effective S process production. But that's not all. There's still other experiments to come. There's a Helios measurement, which I'm not going to mention, but there's very similar to the experiment that we're currently running, which is neon-22. There was a previous measurement done with Emma Tigris and a silicon detector here here at Triumph, but again, trying to measure the oxygen-17 alpha-gamma reaction indirectly at low energies where the direct measurements are not really feasible. And so this is sensitive to the alpha-gamma reaction in particular, and not only to, say, the alpha particle widths like the Munich measurement. So this is a really nice complementary study to some of those previous experiments.
Excuse me,
so
Phil. Just a reminder, 5 minutes left.
Yeah, I've got about 2 slides left. I'll be very quick. Don't worry. These are data from Cameron and Matt, and I should point that out now because none of this is my work. But you can see some really nice structures in here where there's, for example, the excitation energy against the gamma ray energy, and you can see the kind of direct to ground transitions from these data and things. And so the analysis for this is ongoing. They're using these coincidence techniques to try to resolve the contribution of some of these low energy resonances to the alpha gamma rate. And you can see, for example, if you gate on some excitation energies, you can see the gamma rays associated with the de-excitation of those excited states in Tigris as well. So this is a forthcoming result, which will help us to reduce the uncertainties, the remaining uncertainties on the oxygen-17 alpha gamma reaction rate as well. And I'm really looking forward to seeing these data come out. So my concluding remarks, I think that with the nuclear data that we have from these various different experiments, we can show that we can produce some elements above strontium in the rotating stars. We have a lot of experimental tools for probing these reactions. It's a lot of effort to go to, but it's really important that when we have all of these experimental tools, that we are able to kind of, it's almost like Sudoku, but in more dimensions. How do we make a holistic understanding of the nuclear data from all of the different experiments? I'm sure, given this is an IRENA talk, that I'm preaching to the choir, but it's very important that we have a robust nuclear experiment to nuclear data reaction rate astro-model pipeline. That's, we're not just doing these experiments for fun. We need to make sure that we can propagate our experimental data through to astrophysical models with reasonable uncertainties and all of those other caveats. And I think what I'm hoping I've convinced you of is that programmatic efforts using lots of different reaction techniques to try to tackle the same nuclear problem are really important. And so combining different things, combining different experiments is a really vital thing to be able to do. And just before closing, I just want to mention again, most of this work has been done by other people. And there's many papers, there's astrophysical background papers as well that come into all of this, which I haven't really discussed so much, but I do want to mention the people on this slide who have either done the data analysis or done the calculations or done lots of the background work for all of this. And if you would like more information on the experiments which I've discussed in this talk, the citations to the relevant papers are these 4 down here. And with that, I shall stop talking.